Okay, so now that we have a little bit of the formalisms of the necessarily that covalent bonds aren't actually perfectly covalent, that they're often asymmetric, and we call that that notion polarity. Um, we need a new sort of tactic or formalism to actually draw these structures out to indicate where the electrons are and where they're being shared in bonds and where they're not being shared in bonds. And so many of you might remember this. This is a sort of key part of starting to learn the formalism of drawing structures of molecules. We use these things called electron dot structures or electron dot diagrams. We also call these things Lewis dot diagrams or Lewis structures. They're all the same thing. I'll probably call them both interchangeably, just depending on what I'm talking about. And really, these structures are two-dimensional representations of how electrons are going to be shared in a molecule. And by shared, we mean where the bonds are and where the bonds aren't. And the driving force for all of this, our operating principle, is going to be the same as the one that we talked about when we talked about ionic compounds in chapter 6. All atoms are really trying to share electrons. Instead of giving them away completely like in an ionic compound, they're going to share them in order to achieve that perfect octet of the valence set of the noble gases. So Lewis structures, we're going to draw out the valence electrons. Remember, the valence electrons are those that are contained within the highest principal quantum number, or n, shells. So we're going to draw those out explicitly, and the reason we're talking about valence, and we alluded to this back when we were talking about this in a couple chapters ago, was that valence, these are the frontier, these are what interact with other atoms in space. And so the core electrons, those that are not in the highest principal quantum number shell, those remain largely unchanged through interactions. They're really stabilized because they're attracted to the nucleus. Those valence electrons, they're way out there in space, and those are what we're going to consider for the bonding electrons. So let's start simple as always, and let's consider just the hydrogen atom. So we know hydrogen is just a proton and an electron. So if we've got two of these things together, the Lewis structures of hydrogen would look just like this. We'd have hydrogen with one dot representing that one s1 electron that each of these hydrogen atoms has. So these are the valence electrons. We note them as a dot like that. And we can draw them together, coming together and forming this bond. And in this case, hydrogen is going to share one electron from one atom and another electron from another. I'll just draw that in a different color to form this covalent bond right between them. So that is the covalent bond that forms between hydrogen. And so now collectively, this each of these hydrogens can be thought of because you can think about it from the perspective of this first hydrogen. We could say that first hydrogen, it's thinking it has both of these electrons. And so if it has both of those electrons, that's great because now it's got a full shell and it's 1s2 instead of 1s1. We could also think about it from the purple hydrogen perspective because it also thinks that it's got a full shell. Even though neither has fully given the other, they're both sharing these electrons, and so each gets to count that shared electron towards its electron count. And in doing so, these have full shells of electrons. This is not an octet because we talked about before. An octet is when you have a configuration that looks like this. And that octet is what all atoms strive for, right? To have that full shell. But hydrogen atoms can never have an octet because they don't have enough electrons to fill out that p orbital. So hydrogens are a little bit unique in that we consider this satisfying the duet rule. So hydrogen, if it has a 1s2, it's got 2 electrons in its 1s orbital, that's satisfying the duet rule, which is essentially equivalent to the octet rule for all other atoms. And so we're really operating on the premise that when atoms bond to each other, they're trying to satisfy either the duet or the octet rule. And we're gonna use these both quite a bit going forward. We should also note then that if each of these hydrogen atoms is thinking about its electron configuration by including both electrons, then these full shells are both noble gas configurations of helium, which is good, right? Those are happy atoms, which is why we end up forming hydrogen gas as opposed to staying as hydrogen atom. That's a net decrease in energy because we're going from 1s1, which is a fairly unstable, unpaired electron, to fully filled shells. So let's think about a second example here. Let's think about fluorine and fluorine bonding to itself to make F2. Let's write out the Lewis structures of each of these. So to do this, start with the fluorine atom. And so fluorine's all the way over here. We can write out the structure or the electron configuration. We'll just do it as a closed shell because we only care about the valence electrons anyway. So we have helium as the closest filled subshell, and then we have 2s2, 2p5, 2s2, 2p5, and we would have two of these atoms, right? So we could draw this up. This would indicate that we have a total of 7 valence electrons in this n equals 2 principal quantum number. So we could draw out fluorine as 1, 2, 3, 4, 5, 6, 7. That would represent all of those valence electrons that are available for forming bonds. And we have 2 of these, right, to form F2, fluorine gas. And so we'll have 2 that look identical like this. So you can imagine what's going to happen here is that electron from this can be shared to fill that. This electron can be used to fill this. And so when these two combine, what we end up with is fluorine, where you have a bond that's shared between them based on the sharing of those 2 electrons, right? And so now each of these fluorine atoms has this complete filled subshell. Now they're 2s2, 2p6 for both of them, which is the same as the neon closed shell. And how many electrons are around each of these fluorines? Well, each fluorine counts those shared electrons for themselves. So we'd have 2, 4, 6, 8 on the left fluorine, 2, 4, 6, 8 on the right fluorine. What's unique about 8? 8 is that octet, which is telling us that we have a full shell. So both of the fluorine atoms have the completed octet here. So this is going to be generally true for any of these group 7 atoms, and when they form the diatomics relative to themselves. This is always going to be the case. So group 7A looks like this. Substitute in chlorine, bromine, whatever. Let's think about group 3A really quickly. Group 3A is this weird one, which we'll talk about in the next chapter why this is the case, but let's think about boron. So group 3A is over here, so this is boron. So how many valence electrons does boron have? Well, let's just write out the configuration. So boron's got the closed shell configuration of helium, and then 2s2, and then 2p1. So it's actually got 3 electrons to share as valence electrons. So we could write out boron here as 1, 2, and 3. The general way to write Lewis structures, and I didn't mention this explicitly before, is to fill electrons one at a time on the 4 sides of the symbol. And then if you have more electrons to add, in the case of like 7 for fluorine, then you start pairing as you go until you wrap your way around. You can only ever have 8 on a typical main group element. Okay, so boron's got these 3 valence electrons. That makes it a little weird. So let's think about it if it bonds with, say, hydrogen, which has 1. So obviously these are going to jump over here, and this is going to make this compound boron that'll form a bond with that one, a bond with that one, and then a bond with that one. But at that point, it runs out of electrons that it can share with, right? It doesn't have a 4th one that it can form a 4th bond. So in that case, we can look at hydrogen, and hydrogen in each case has a 1s2 filled shell, so it's satisfying the duet rule in each case. But what about boron? Boron, in this case, only has 6 electrons associated with it instead of the 8. And so group 3A is this exception that doesn't follow the octet rule. So anything in that group 3A here, because it's only got those 3 valence electrons, it's sort of in this middle ground. It can't form that 4th bond, which would give it its full octet. So group 3A exceptions don't follow the octet. We'll talk about why that exactly is either at the end of this chapter or at the beginning of the next. This is actually still a really stable compound, even though it doesn't have 8. But we don't have the concepts yet to rationalize why that would be. All right, let's just jump over one group here to group 4A, and hopefully you're seeing a trend here. So when you're in group 3A, how many valence electrons do you have? You have 3, because you have the NS2 is filled, and then you have NP1, so you've got 1 in the P, so a total of 3. If you move over to group 4, you've got 4 valence electrons. You go to 5, you've got 5, 6, 7, and 8 valence electrons, right? And so we could write out the electron dot diagram if we forget, but we don't need to. We could just look up here and know, and this will become second nature as you start to play around with these quite a bit more. So let's think about carbon. So carbon, again, would have a closed shell configuration of helium, and then 1s2, not 1s2, sorry, 2s2, 2p2. That's that 4 valence electrons that we'd said anything in that group 4A would have. So we just confirmed that. So we would write that up as carbon, and then 1, 2, 3, 4. Remember, we don't pair them until we get past 4. Then we start to pair them up. So we have carbon like that, so we could tack on, say, its reaction with hydrogen, which again has just 1. So those 4 are going to come pair up like that, and so we're going to end up with carbon and then hydrogen on all 4 sides. So we'll form 4 bonds like that. You can look at this and you can see that each of the hydrogens has this nice 1s2 duet, so it's filled. Those are happy. We could look at carbon. The electron configuration for carbon then is going to be 2s2, 2p6. I'm sorry, this shouldn't be 6. This should be 2p2 here. Sorry if that was confusing. Okay, so that's a happy octet for the carbon, and it's a duet for hydrogen, so that's going to be the case for really any group 4A. And so the general theme here is you figure out how many valence electrons each of those groups of elements has, and then you can tack on as many additional elements or atoms to share electrons such that that central atom achieves its full octet, and ideally the peripheral atoms, in this case hydrogen, either satisfy their octets or their duets depending on the nature. So we're going to do this with a whole bunch of more complicated examples. We're just sort of laying out the general framework now. Alright, so let's look at group 5A here. So that's starting with nitrogen. So that's 5A. We know now that its group number also corresponds to how many valence electrons it has. We could write out the configuration, but we won't. So group 5A, it's got 5 valence electrons. So we have nitrogen, 1, 2, 3, 4, 5. That one's paired there. So if you look at it, it only needs 3 more electrons. It's got 5 to start. It needs 3 to form a nice octet. So in that case, it can only react with 3 of these hydrogens. And in doing so, it's going to create nitrogen and then hydrogen bond there, hydrogen bond there, and a hydrogen there. But it still has those electrons right there that were paired up, and those end up being non-bonding. They don't participate in any bond. They're just hanging out in orbital on nitrogen, but they don't actually get shared across any other atoms. We call those lone pairs, and this is going to be the case for anything in group 5. It only needs 3 electrons to make that octet, so it'll form those 3 bonds by sharing up another electron with another atom, but then it's always going to have this lone pair there, at least in the neutral state. All right, jumping over to group 6A here. 6A meaning it has 6 valence electrons. For instance, oxygen is what we've got here. So I've got 2, 4, 6. Those are the purple dots around oxygen. Just like nitrogen, we can say, well, it's already got 6. It only needs 2 more to make that octet. So it's only going to be able to react with 2 additional electrons. In this case, the example is hydrogen, in which case we're going to be able to make something that looks like something you're pretty familiar with. So, oops, I didn't mean to make a line there. We're going to erase that. Oop, can't erase that line. That would form a bond, a shared bond with hydrogen there, a shared bond with hydrogen there. But that means we still have these non-bonding pairs, these lone pairs, hanging on up here. So what is this compound? Well, that's water. And I should also note that I mentioned this before. We could represent the compound like this, or more often it's easier to represent those shared electrons between atoms as lines. Those are equivalent. So these double dots here and these lines, they mean the same thing. And I'd also need to add my lone pairs here. So it's more common, especially when you get more complicated molecules, to just use lines to represent that. I should also state that some people, you may see this in your textbook or in other videos, some people will even write their lone pairs that way. So they might write water like this, where the bonds are that way, and then they may have 2 lines up here where those lines are essentially representing those 2 lone pairs. Whatever you want to write, you can do that. But the general takeaway for group 6 is that it only needed 2 electrons to make that nice octet, which means it's got 2 lone pairs hanging out on it. Those 2 lone pairs, we'll talk about in next chapter, have huge implications on how the shape of water is dictated and ultimately its chemical and physical properties. All right, last but not least, we've got group 7A over here. So these are the halogens. 7A meaning it's got 7 valence electrons. So I'm using fluorine as the example. So 2, 4, 6, 7 around this, which means it can only take 1 electron to make the octet. It's only going to react with 1 equivalence of hydrogen, and it's going to make something that looks like this. So fluorine, and then it's got the covalent bond between it and hydrogen. But then, of course, it's got now 3 sets, 3 pairs of lone pair electrons. We could write this out like this. This would be a more formal way to write it, probably more common to look like that. So that's hydrofluoric acid. So it's got 3 lone pairs hanging out in space, unbonded, but it still has the satisfied NS2 NP6 NP6 octet, and hydrogen here has that nice 1s2 duet. So we've got the octet and the duet, and so anything in group 7 is going to obey this general type of bonding scheme where it can take on 1 spare electron to remain neutral, I should say. So that leads us to the sort of final takeaway point, which is shown in table 7.4 here from your textbook. If we're looking at these second row elements, all of the ones that are, well, let's see if we can drag this down a little bit. All of the ones that we've been talking about thus far have been up here in row 2. So boron, carbon, nitrogen, oxygen, fluorine. All of those, depending on their group number, if they have a group 3A, it has 3 valence, which then means it forms 3 bonds. If it is group 4A, it has 4 valence electrons and can form 4 bonds. At 5A, it's got 5 electrons, but that means it's got a lone pair there, which means it can only accommodate 3, 6, 6, and 2, 7, 7, and it's just got that 1 bond that it can form, and then 8 would be noble gas. It's already happy, doesn't form any bonds. That's something like neon, argon, krypton, etc. So what about multiple bonds? I mentioned this before, but if you've got something like oxygen gas, which is this first example, this is oxygen, this is nitrogen. So for oxygen gas, it's group 6A, which means it's got 2, 4, 6 valence electrons on each, 2 of which are unpaired. Those 2 unpaired electrons can come together to form 2 sets of shared electrons, or 2 covalent bonds, which gives us that double bond. The same can be true for nitrogen, right? Nitrogen is in the group 5A, so 1, 2, 3, 4, 5, 3 of which are unpaired. Those 3 unpaired electrons can all come together, form 3 sets of shared electrons, and we've got that triple bond.